Hello, this is Module 4.4 MOSFET Amplifier Topologies. So the module coverage is shown here. So first off, we're gonna talk about amplifier basics and then the characterization and design guide for amplifiers, basic MOSFET amplifiers, the common source, common gate, and the common drain, and how to choose a cue point. So first off, base amplifier basics. This is just a review from Module 3. So the amplifier aims to achieve amplification. So what is amplification? It increases the magnitude of the signal while maintaining signal information. So one benefit of this is it allows weak signals to be processed accurately and reliably. So the basic idea is if we have X as the input signal and Y as the output signal, you will get this relationship here. So Y equals AX, where A is the gain. So looking at this graph, we have this transfer characteristic curve for Y equals AX. So as you can see, it is a straight line. So ideally, the gain should have a constant value and have this kind of transfer characteristic curve. Otherwise, the information is not preserved, which means most likely that the output signal will be distorted or not have the same signal information as the input. So, signals. So how do we define signals in an amplifier? So first off, the quantities defined by capital letters, so of course we're considering voltage and current, are DC signals. So these signals are usually used to denote peak quantities or bias quantities, which defines the cue point. So cue point is defined to be the quiescent point or operating point of the amplifier. So in this example, this is taken from module 3C. The DC quantities are this one, which shows I, capital I, small c. So when we have this kind of signal, this is a peak amplitude. And then if we have capital I or capital C, so this means that if both are capital, even the subscript letter, this means this is the DC level. So this is the average signal. So as you can see, this is a sine wave, and capital I, capital C is the average of this signal. And when we have a capital I and a small, it considers to be the peak. So this is defined to be it. And then quantities defined by small letters of small v or small I are AC signals. So these signals act as the actual sinusoidal input, so the signal to be amplified or output, or the amplified signal quantities of the amplifier. So from here, you can see that when we consider small I and a small subscript, so for example this one, small I, small c, this is the varying amplitude. So this is the pure AC signal. So this has no DC offset. So now, if we change it to a capital letter, the subscript is changed to a capital letter, this is now the AC plus the DC offset of the signal. So we're gonna use this signal identities or signal norms in this course. So as an example, we're going to show it here. So if we have an input signal, VI, capital VI and I plus small v plus small I. So this is the AC signal and this is the DC offset. And then, of course, it will be amplified to a certain value. So you will get some output DC, capital V, capital O, and small v, small o. So what does this show here? So from this graph, we will show how the relationship between these quantities here. So for example, this one. So remember, capital V, capital I is the DC, the average. So it's here. It's in the middle. And then the small v, small I defines the sine wave shown here. So it will be amplified to some certain V out. So this is the DC output, V out. And then the small signal, the small V small out is the sine wave that will be shown here. Okay, so important notes. commonly in an amplifier, the DC input voltage is not amplified. So because the capital V capital I quantity, the input side, defines the bias point of the amplifier, which defines how the amplifier operates. So in order for you to understand this more, we're going to discuss real amplifiers later. But the point is, you do not amplify the DC bias, which is this one, the bias point. And what will be amplified? The amplified signal is the small v small I quantity here. So you get V out equals A V in, where A is the amplifier gain. So take note, V out is just the DC bias here on the output side, the DC bias. And then the AC signals can be any periodic signal, square wave, sinusoid, sawtooth, etc. So what will be the guide for amplifier characterization and design? So how do we characterize and how do we design amplifiers? So a simple method is to use these steps. So the first step, usually, if we have an amplifier on hand, is we find the voltage transfer characteristic, or let's just call it VTC. So that is V in versus V out of the amplifier circuit. So how do we do this? We just sweep the input and find the output and plot it in a V in plus V out plot. So as you can see, these are all capital. So you just do DC analysis. So just like what we did in module 4.3. So that's where we're just going to repeatedly do that. And then we find the gain function. So the gain function is just the derivative of the output with respect to the input. Because as you remember, it's just V out over V in. And also, you consider that the gain is a slope, right? So if we have a V in versus V out plot, we just need to find the slope and we will find the gain. So if we do this, we'll get a V in versus V out, V in versus gain plot. And then, from these two plots, we can choose a suitable Q point depending on desired amplifier specifications. So because we expect that the amplifier will not have an ideal linear behavior, so it means that it depends on the DC value of the input with what gain and what voltage swing will the amplifier have. And then if we choose a suitable Q point, we can now characterize the other properties of the amplifier. So we can characterize their small signal parameters, their frequency response. So small signal parameters will be discussed in the 5th module, the next module, and then frequency response will be discussed in module 6, the final module of this course. And also, for future advanced topics, we can also characterize the transient response. So rise time, fall time, settling time, etc., etc. And then, if we get all of these steps 1 to step 4, and we did not get the ideal amplifier specification stated, we can redo the design of the amplifier by changing the other parameters. So instead of changing the Q point, we can change the type of resistor, the resistances, the loads, and then we can redo step 1 to step 4 again until we get the desired specification. So this is an advanced topic and will not be covered in this course. So now, let's move on to the types of MOS amplifiers, basic MOS amplifiers. So this is the common source amplifier. As you can see, this is the NMOS equivalent and this is the PMOS equivalent. So why is it called common source? It is because the source, so remember that the source is the terminal with an arrow, is common to calculate the VGS and the VDS of the amplifier. So as you can see, VGS is V in minus the source voltage, and the VDS is V out minus the source voltage. So it is common to vote VGS and VDS because the source does not change. Same concept here. So the VGS is, well, for the PMOS it's VSG, right? So it's VDD minus V in, and then for the VSD it's VDD minus V out. So remember, the common source amplifier occurs when the source is a constant and is common to both VGS and VDS because it's constant. Okay? So now, we're gonna do the VTC of this amplifier. So remember, step 1 is to find the VTC. So what are the important equations? So first step is to find the KVL at the drain loop source. So it's negative VDD plus IDRB plus V out, right? And then if you solve for the output voltage, is V out equals VDD minus IDRB. And then, of course, remember, we need to find the region of operation of this amplifier. Therefore, we must find VGS and VDS. So as you can see, VGS is simply V in, then VDS is simply V out. So from these equations, the voltage transfer characteristic can be found by plugging different values of V in and determining V out. Take note of the region of operation for every value of V in. So this will be the voltage transfer characteristic of this amplifier. So now, what is the important thing here? The important points. So the first important point is this one. So remember, if this amplifier is biased, so if we introduce a V-in that is less than the threshold voltage, it will be off. And if this is off, there is no current, therefore it remains VDD. So in cutoff, it remains at VDD. And then, if we increase the value of V-in to be greater than VTH, the drain current is increasing. And remember, this will be in saturation because it started off from VDD and it goes down. And we expect that this will be greater than VDSAT. So that's why it's going down, because ID is also increasing. And then, if we reach the output to be VDSAT, then this will be in the linear region. And remember, we cannot pull this to be negative, so it will be asymptotic to 0 volts. So this will be the voltage transfer characteristic of the common source. So now, if we find the gain function, if we want to find the gain function of this, we just have to find the derivative of this function. So if we find the derivative of this with respect to V-in, we will get dV out over dV in is equal to negative dID over dV in RV. So remember that dID is this one, and it is increasing with respect if we increase Vn. So that means when it is getting more negative. So that's why it looks like this. And then it reaches a peak and then it goes back down, because remember, during this point the slope decreases significantly. So that's why you can look, you can see this one. So at cutoff, we expect that the gain is 0, and at linear is almost 0 or very, very low. And mostly, the gain can be seen when the amplifier operates in saturation. And there is a peak here called Amax. Let's name it Amax, which is the maximum gain. So as you can see, because it has a negative gain, therefore, this is an inverting amplifier. Okay? So now, let's go to the common drain. So the common drain amplifier, so how do we find out if this is a common drain amplifier? So first off, we look at the drain. So this is the drain. So this is an NMOS, this one. So it is common because remember, this is constant. And also look at this. This is also constant, right? Constant to both sides. So from here, we can see that we can also calculate the VTC of this type of amplifier. So if you consider this common drain for an NMOS, we can calculate it using pertinent important equations. So VDD minus V out minus VDS equals 0. Okay? And then V out is just simply IDRB. Remember, there is no gate current, so it's simply IDRB. And remember that we need to find the region of operation of this amplifier, so we find VGS and VDS. So VGS is simply V in minus V out, and then VDS is simply VDD minus IDRB. So we're just going to do what we did earlier. We're just going to sweep the value of input and find the output. So we will get this. So now, as you can see, what's important here, if we have Vin less than VTH, so if we put Vin less than VTH here, we will get zero current. So because V out is IDRB, we will get 0. And then if we keep increasing Vin, because if we keep increasing Vin, the current increases, so we get upward here. And then we will reach the linear stage of the amplifier at VDD minus VDSAT. So how did we get this? Because if we substitute VDD minus VDSAT here, if we find the voltage across here, we will get VDSAT, right? So that's why it is here. And then it goes to the linear region. And remember, the output cannot exceed VDD here. That's why it looks like this. So as you can see, if we find the gain characteristic of this, we will get something like this. So the common drain amplifier has a gain characteristic like this. So remember, cutoff, nothing changes, so it has 0 gain. And then the linear side is almost 0, very, very low. And we have a max. So as you can see from here, it almost looks like a straight line. So we will get something like this. So a constant, so the derivative of a straight line is almost a constant, and it's usually less than 1. And as you can see, because the gain is positive, this is a non-inverting amplifier. Lastly, if you look at the common gate, so remember, in order for us to find out if the amplifier is a common gate, we look at the gate, and mostly it is a constant. This. See? So, for the NMOS, it looks like this. For a PMOS, it looks like this. Then let's repeat the process again. So let's consider a common gate using NMOS and find the transfer function. So what are the important equations? So KVL at the drain source loop here. So VDD equals V out plus V in. And then V out is simply VDD minus IDRB because we need to subtract the voltage drop here. Remember that ID is dependent on VGS and VDS and the region of operation, right? So we're going to look at VGS, which is negative V in, and VDS is V out minus V in. So what is the transfer characteristic? It is this one. So as you can see, because Vn is negative, we want a value more negative. Okay? We need a value more negative to turn this on. We cannot make this positive because this is ground. So we can find that this will be the equivalent transfer function or transfer characteristic. So when the transistor is in cutoff, when the Vn is between 0 and negative VTH, because anything less than VTH here will have a VGS less than VTH, so that is cut off here. And then if we increase the value of Vn, ID, or we increase the magnitude of Vn to be more negative, so increasing here, so we will get ID will be increasing, so this goes down here. And then as you can see, if we reach the linear stage when we have VDSAT in VDS here. And then we go. So what if we find the derivative here, we will get this. So remember, because this is in reverse, so it's more negative. So even though this has a negative side, negative times negative is positive, we will get this kind of gain function. And same as the common drain, this is a non-inverting amplifier. And something to think about is during cutoff, it has no gain. During the linear stage, it has no gain. But almost gain, the gain can be maximized when the transistor is in saturation.